It's a pleasure to be part of this conference. As a practicing solar physicist, I work on several of solar missions that I'll describe today, and it won't be an exaggeration to say that observations from space revolutionized our understanding of the sun. Instruments that observe from the ground see the universe, the sky and the sun, through a narrow optical window and through radio and microwave, only those two wavelengths. The rest of the radiation is absorbed by the Earth's atmosphere. In particular, the highly important far ultraviolet X-rays and gamma rays are all absorbed between 20 and 50 kilometers altitude. And we have to send rockets or satellites to observe that radiation. And we know today that the sun emits radiation, the light, across the entire wavelength spectrum. The largest amount of light comes in the visible light, but there is a significant amount of photons arriving in these extreme ultraviolet and X-ray wavelength. In fact, there are thousands of spectral emission lines emitted in the X-ray range. And all of this was totally unknown in the 40s. This part of the spectrum was a blank chart. It waited to be discovered. The history of observations from space can be divided into three periods. 1950s and 60s was the age of first rockets and simple satellites. From 1973, we had a large Skylab observatory and several well-equipped missions studying mostly flares. And from 1991, we had modern missions, superbly equipped with ever more sophisticated instrumentation. And several of them are operating today. So first, I'll move very rapidly through the first 20 years just to get a feeling for what was discovered starting virtually from nothing until the launch of Skylab. So various rocket launches started after the Second World War brought the understanding that the sun emits X-rays, and in fact emits even more powerful X-rays during solar flares. It also emits gamma rays. These are highly energetic particles. And the very first spectra in the invisible range, called extreme ultraviolet, were taken, and that was a great achievement. If you are afraid of spectra, think of them as uncolored rainbows that await an artist to color them. They have these vertical white streaks, which are spectral lines. And when this was discovered at the end of 50s, scientists immediately identified that there are elements on the sun, the same as here, in the sun's atmosphere. Hydrogen, helium, carbon, oxygen, nitrogen, magnesium, calcium, iron, everything we know here on Earth as well. And they emit those spectra. And so that gave the momentum to improve the quality and keep extending this towards shorter wavelengths. And even the very first X-ray image was obtained, but using a very simple technology. So it didn't really look impressive, and it suffered from a rotation of the rockets. It was smeared out. But the very fact that they discovered this radiation was hugely important. And then the technology of observing X-rays improved. A new grazing incidence optics was designed, and in a quick succession from 63 to 69, there was a rapid improvement in the quality of the images of the sun, from those fuzzy, noisy images to those at the bottom, which were very respectable images of the sun's corona, and showed it in a way we've never seen before, with concentrations of brightness, with dark regions, and even little tiny bright points here. So there was a lot of preparations in those 20 years, and the observing techniques were being developed in all areas of X-ray and ultraviolet observations. On the other hand, in parallel, satellites were being launched after the first Sputnik satellite was launched. They were initially small, so carried only small detectors. Later, NASA commissioned orbiting solar observatory, 6 of these spacecraft, which weigh 200 kilograms and more. But the imaging instrumentation of these spacecraft was actually a bit inferior compared to rockets. So rockets were winning in terms of bringing high quality images. And however, also 7 satellites in 721 detected clouds of material leaving the sun. That was exciting. They were called coronal transients at that time. And also observed some gamma ray lines. That's very intense radiation during flares. Oh, that's a replica of the British satellite, Ariel 1. So at that point, in 1973, the first US space station was launched. Skylab was initially launched as an unmanned observatory, suffered an accident and damage during launch, and subsequently 3 crews of astronauts visited observatory. The first crew repaired the damage, and the second and third crew did most of the observations. There were 8 solar instruments on board. That usually consists of X-ray telescopes, ultraviolet spectrometers, visible light imagers, coronagraphs. In total, they collected 160,000 images. They were all taken on film, and astronauts carried them back to Earth. And these instruments were housed at the end of this module called ATM. That was Apollo Telescope Mount, where they all were observing. And astronauts were trained to operate them. These X-ray images from one of the X-ray telescopes summarize the essence of the discovery of Skylab of the sun's X-ray corona. What we see are 4 components. These bright, compact regions here, they are called active regions. The more moderate intensity, brightness, this is generally called quiet sun. Then we have points of light that were given name bright points, and these extended dark areas, they were void of X-ray emission. To explain the significance of these features, I have to mention the presence of an invisible agent, a medium called magnetic field, which permeates the entire corona all around the sun. It's generated deep in the interior of the sun, it rises to the surface, spreads as field lines into the corona, and creates a complex web of field lines. And the active regions, the bright areas, are typically concentrated, or always concentrated, above these strong magnetic field concentrations. The negative and positive polarities, black and white, is a strong magnetic field on the surface of the sun, measured by other instruments. This is a modern image from not so long ago. And active regions connect these 2 opposite polarities. The middle images show a life of an active region which lived quite long, about 2 or 3 months. Typically they disappear after several weeks. You can see how it fades away, and then gradually there's no trace left. But these elongated features here are so-called coronal loops, and that's what Skylab discovered. They connect these 2 black and white polarities, and these are magnetic field lines keeping the plasmas. And plasmas get hot, and then we see them as these elongated features. There were more loops to come as the astronauts were trained to spot interesting things on the sun. So they found on the limb these lovely semi-circular structures, the loops. Here we see a bunch of coronal loops edge on. And when looking down on the sun, on the disk of the sun, there are arches of loops shown here. And since then, a field, theoretical and numerical modeling of these coronal loops flourished. For the last 30 years, a lot of solar physicists keep busy modeling these features. The bright points, on the other hand, lots of these can be seen up to 100, are short-lived, 8 hours on average. They are located above small concentrations of magnetic field. The significance of the coronal holes is immense. They are very different. They contain magnetic field, which is unipolar, of one polarity dominates inside, and the field lines stretch out, they are open, stretch out from the coronal holes all the way radially into space, and they are carried out to fill the entire solar system, the entire heliosphere, and they are also being wound up because the sun rotates, creating a spiral of those magnetic fields. And the second reason they were important is they constituted a solution to a long-standing mystery. What are the sources of high-speed charged particles that were seen in space? This is now called solar wind. It was recorded by Mariner 2 spacecraft in '62. And solar wind comes in two varieties: a slower moving, 300, 400 kilometers per second, and a fast solar wind at 700 to 800 kilometers per second. And it was particularly this fast wind that perplexed scientists. They knew it must come from the sun, but where exactly from on the sun, it wasn't known. And these images are taken 27 days apart after each full solar rotation. So that coronal hole lived for at least 3 months. It started to close down, but it was still there. And as it returned to disk center, another probe called Interplanetary Monitoring Platform near Earth recorded these high-speed streams. So that correlation between the appearance of the coronal hole there and the high velocities in the solar wind was a proof that that is the source. That's what's surprisingly ejecting these invisible charged particles, protons, electrons, and other ions traveling fast in space. Other instruments on Skylab were spectroheliographs. They spread the light into wavelengths. They have a device called grating. They do act like producing these rainbows. And this one was called slitless spectrograph, with the effect that for each spectral line it was producing a disk of the sun. And each of these lines was emitted at different temperatures. So there were temperatures of 50,000, 500,000, and 1,000,000 degrees Kelvin on the sun. So we had slices, temperature slices of the sun's atmosphere. So that was something rather unique and gave the scientists years of excitement to describe and understand how the sun's atmosphere operates at all those different temperatures. And when another spectrograph inserted a very narrow slit in front of the grating, the disks, the images of the sun disappeared, and what was left was a pure spectrum. And that was taken during a solar flare and produced nearly 5,000 spectral lines. All those black streaks are spectral lines. So it's spectroscopist heaven. Some of my colleagues, now very old, spend their careers trying to describe, identify this, and understand what is actually happening during solar flares. And flares, examples of them at different temperatures are shown here. This is what happens in a coronal loop. At the top, it becomes very bright in X-rays, but that's high in the corona. At the same time, very low down in the chromosphere, you see these flashes of light. And this is all like interplay of energy. Energy is released in one place, it's dumped low down, and it creates a lot of motions and all sorts of different phenomena. So quite complex but fascinating phenomena. And this is just after they finally digitize this, we see lovely line profiles, which can be measured and studied to derive these parameters. Other important features of the Sun are prominences. They were seen in the visible light as far back as 19th century, above the limb of the Sun, but Skylab saw them at higher temperatures in the light of singly ionized helium, which said that plasmas in those prominences have 50,000 degrees Kelvin, not only 6,000 as seen in the visible light. These features are supported by the magnetic field, so lots of material there, mostly hydrogen and helium, of course, supported by the field, but field can become unstable and swing out into space, throwing out all this matter. And one of these eruptions was caught by a Skylab camera here in the process of being ejected from the Sun. And that leads to these coronal transients that also 7 saw for the first time. If you look at this light bulb shape, this is what we today call coronal mass ejection. It was this transient. The Sun is hidden behind the black occulting disk, so this shape is bigger than the Sun itself, and it keeps growing as it moves the field of view and travels out into space. There can be other shapes, more rare but equally weird, with twisted field lines and entangled structures. The interest in flares stimulated the development of at least 3 missions by the end of 1970s. One of them was SMM, Solar Maximum Mission, had 7 instruments to study flares, mostly through spectroscopic means. It also had an interesting story of malfunctioning and being repaired by Space Shuttle Challenger. One of the spectrometers, and I have to raise the UK flag here, because there were 2 UK principal investigators leading this instrument, was called Bent Crystal Spectrometer. It produced these lovely spectra in X-ray emission, which are emitted only when the plasma is very hot, 15 million degrees and higher for this calcium spectrum, and 18 to 25 million degrees for the ion spectrum. Incredible temperatures, but can be measured using ratios of some lines in the spectrum. So this is one of the superb results from SMM to measure these spectra during flares. SMM also had a white light colonosgraph with much better rejection of stray light, so the contrast was good. It found a better structure, a very fine detail of these mass ejections. Again, you see these lovely shapes of semicircular. This stimulated more theoretical research to explain them, but a thorough study using this data found what comes first, a flare or a mass ejection. And contrary to popular opinion at the time, they concluded that the first comes the launch of a coronal mass ejection. Only 20 minutes later, a flare happens, which matters to many of my colleagues. The next modern mission was the Japanese Yoko, launched in 1991. It had a set of 4 instruments. One of them was called Soft X-ray Telescope, with very good resolution, and it produced these images of the Sun in X-rays, far surpassing anything that Skylab has seen, particularly that this was the maximum of the solar cycle, and the Sun was very busy in the corona, with many active regions, many coronal loops, lots of flares taking place. It found also why mass ejections happen. some active regions have an S-shaped field, and they tended to erupt after a few days. So S marks the spot was the title of the press release, which excited even the public. Yoko observed for 10 years, and until it was lost due to another accident. It saw the sun during the minimum of the solar cycle in '96, where the sun almost has no active regions, just quiet sun and hundreds of bright points and two coronal holes in the north and south. And here is the maximum of the cycle with several active regions at a time, each creating lots of flares, and generally it's a very violent place. An improved version of this Bragg crystal spectrometer from the SMM, again built by UK groups, was flown on Yoko, and they continued studies of an interesting thing. At the very beginning of the flare, they saw the profiles of line moving rapidly far to the short wavelength. They were blue shifted. That meant that a lot of plasma is rising from the bottom of the loop, we call them foot points, up into the corona with speeds 300 to 400 kilometers per second. This was given a name chromospheric evaporation, and that was distorting these line profiles, making them asymmetric. They were bulging on this side. And these were like violent motions happening at the beginning of almost every flare. So again, that was helping to understand what happens in flares. In 1995, ESA, that's the European Space Agency, and NASA launched the Solar and Heliospheric Observatory. It's the biggest ever space observatory. It had 12 instruments on board, provided both by European and US groups. And the science goals of SOHO were to study the interior of the sun by measuring oscillations on its surface, to understand the heating of the corona and why the solar wind is accelerated in coronal holes. And the SOHO was sent to a Lagrange L1 point, 1.5 million kilometers from Earth, on the Earth-Sun line, where the gravitational pull of the sun and the Earth cancels out, and the SOHO is in a halo orbit. It remains there for the past 20 years, and some of the instruments still work. A group from my laboratory, rather the Atherton lab, led a spectrometer that was observing in the extreme ultraviolet wavelength in 6 bands. 2 of them are shown here. It could measure temperatures, densities, and primarily velocities. Those blue and red patterns are velocities, red shifted and blue shifted, that is either moving to your left or to your right, depending on where the plasma flows on the sun. And all kinds of motions were discovered, either flows along the loop from one end to another, or spiraling motions, or plasma would be ejected as jets, like here, along these elongated field lines. This spectrometer and another sister instrument with different wavelength range discovered oscillations above the sunspots, these nice oscillatory patterns where intensities and velocities would oscillate every 3 minutes. It was later discovered by another mission called TRACE that these waves continue traveling upwards along these extended coronal loops, and that gave birth to a new branch of science within solar physics called coronal seismology. That is the study of waves and oscillations in the corona. Again, it's a flourishing field today. The Sumer spectrometer set out to discover precisely where this fast solar wind is originating on the in the coronal holes. We knew it comes from that area, but where exactly? It measured flows. Those blue patches are velocities concentrated along the boundaries of the magnetic network. The magnetic field emerging in the photosphere creates this honeycomb shape, and the flows were happening along those boundaries, and that was again a crucial finding of the sources of the wind. SOHO has a LASCO coronogram, that's just a generic name for it, which had 3 fields of view. One was damaged when SOHO was lost for a while, but 2 survived and produced superb measurements of these coronal transients or coronal mass ejections leaving the sun continuously. The sun here is the white circle, and this is the larger field of view of LASCO, showing all the time these superb movies of clouds of matter being ejected into space. They found some good statistics. They measured 15,000 of these events. At the solar minimum, there are 45 per month. At solar maximum, 120 to 140, so 4 or 5 a day. So very prolific generation of these mass ejections. So that is quite an impressive finding. There are other quite shocking things in the corona. For example, when a mass ejection is being launched from an active region, immediately it's this big shock wave. This is the disk of the sun. Looks a bit noisy because it's a subtracted image. It's not the real sun. We can see this huge wave spreading rapidly across almost the entire corona. At the level of the photosphere, after some flares, we see these lovely concentric circles, like a stone thrown into the pond, creates these waves. So the sun responds in many strange things to these events. A magnetic carpet was the name given to small-scale fields at the photospheric level, which replenish themselves very quickly. Every 40 hours, we have almost like a brand new field emerging continuously from the sun. And the TRACE telescope that I mentioned earlier was launched in 1998. It had just one instrument, a very long telescope, superbly resolving these coronal loops at 1 million degree temperatures. And they turned out to be very thin, very sharp loops. Here they are seen on the limb, here top down, because TRACE didn't see the full sun, just a large area of an active region. And even more strange features, which are related to solar flares. Here we have, this is the solar flare happening as we watch it. And this is followed by this fantastic, extremely long, huge arcade of magnetic loops emerging and hitting the plasmas and living for quite a long time afterwards. This movie runs much faster than in real time. It takes 4 hours for this sequence. So the flare takes about 20 minutes, and that's the flare for 20 minutes, and then the arcade rises for about 3 hours of actual time. So this is a process that is not as fast as we see it here. So with SOHO and TRACE, this is where I have to draw the line between the history and the present. There have been 4 new missions launched since 2006. Japanese JAXA agency launched the Hinode spacecraft in 2006. NASA launched STEREO in 2006, Solar Dynamics Observatory in 2010, IRIS in 2013. And I have time just to show one result from the STEREO mission. STEREO are 2 spacecraft separating from the Earth in opposite directions. Recently they met behind the sun, crossed over, and they will be returning in the direction of the Earth over the next 10 years. They carry identical payload, and one of the instruments on board is called Heliospheric Imager, which watches the space between the Sun here and the Earth. So the radiation from the Sun is blocked. What this instrument wants to see in its two cameras with the square field of view and the oval field of view are tenuous clouds of mass ejections moving through. They are lovely stars, but they actually get in the way. So what is seen here is the Sun is behind the white circle. When the mass ejection leaves the blue field of view of a coronagraph, it enters the heliospheric imager and can be seen propagating towards the Earth. So this is one of the very first detailed pictures of these mass ejections filling the entire heliosphere in the direction that they travel. And they can occupy a quarter of the Earth. They are massive, billions of tons of matter, speed on average 500 kilometers per second, but can be much faster and slower depending on the type. And those that are directed at Earth, my colleagues at RAL, who actually lead this instrument, track them and try to predict the time of arrival at Earth. I wanted to give a tribute to the Hinode spacecraft just by showing this psychedelic image, but it would actually take too long to explain other than to say that it measured for the first time the presence of very hot plasmas in active regions, 10 million, which were elusive and difficult to spot because there's little plasma of that temperature, but it's very important to know that there are areas of 10 millions in addition to 1 million plasma and say 3 million plasma in other locations. So these temperatures are distributed across the entire active region. And I want to finish by showing two images from the Solar Dynamics Observatory. This is 1 million degree plasma obtained by the telescope on SDO, which takes these images every 10 seconds. And it has also superb resolution, and we can now monitor the life of the Sun almost on a second-to-second basis. It shows these fantastic loops and all the activity that happens on the surface. And if we look at this active region and its life over a couple of days that it takes for it to rotate from the limb of the Sun closer towards the disk center, we can see how these loops change. And also we see, if you look down at lower layer, you can see continuous cannonade of energy releases, various small eruptive events brightening all the time. So if we now compare this to these very early fuzzy black and white images from 1960s to this state-of-the-art imagery, it all happened in the space of just 60 years. And it's really hard to imagine what images we will obtain 50 years from now. Thank you.